Here comes the sky.
Here we go with circular orbits and how we represent circular orbits. We've got, first up, the gravitational field, the effect or invisible structure that causes objects to feel a gravitational force. Gravity works because all objects with mass create an effect around them called the gravitational field. Gravitational field is a type of field which is a physical effect that exists at every point in a three-dimensional space. Every point has field strength associated with it. The field strength is just a number with some units. To imagine the gravitational field, you could think about beads hanging from a doorway. And when you've got the beads just hanging there, hanging straight down, and when you have to go through them, they just move right out of your way. That's what's happening with the field. Gravitational field is a type of field called a vector field. This means that every point not only has a strength, but also a direction, down. The strength of gravitational field is given by the symbol lowercase g. So in other words, we've been using the gravitational field this whole time whenever we use g, the acceleration due to gravity. The gravitational field strength at the surface of the Earth is on average 9.81 newtons per kilogram, but of course we typically are going to use 10. Newtons per kilogram is the same thing as meters per second squared, because remember, a newton is a kilogram times meter per second squared, so kilogram in the numerator, kilogram in the denominator, they cancel out, and what you're left with is a meter per second squared. So when we say g equals 9.8 newtons per kilogram, we're saying every kilogram of an object's mass receives 9.8 newtons of weight force. When we say g equals 9.8 meters per second squared, we are communicating that an object subject to only gravity, an object in free fall, has a velocity that changes by 9.8 meters per second every second. The direction of the gravitational field at Earth's surface is directed towards the center of the Earth. That's why, no matter where you are, gravity points down. Two things the gravitational field tells us. First, the direction, the weight force acting on the object in the gravitational field. In our case, it's always down. And the direction of the acceleration if gravity is the only force acting on the object. That is, the object is in free fall. For any spherical object, the direction of gravitational field is always toward the object center. The direction of gravitational field for any spherical object, or couple of objects that seem to make a sphere, is always directed towards the object's center. This diagram shows a representation of the gravitational field around a sphere, in this case a planet, a small dot. Every arrow has a direction that indicates the field direction, which is always towards the center of the planet. Every arrow has a length that indicates gravitational field strength. Note the field strength becomes weaker with increasing distance. That makes sense, right? Because you have the International Space Station, unless you're watching this in the year 2031 and you don't have the International Space Station. But you get the International Space Station going around the Earth, right? And you've seen videos of the astronauts appearing weightless. Well, they're further away from Earth's surface, so there's less of the field interacting with them. Let's derive an equation that tells us the gravitational field strength at a distance r from planet mass m. Derive an equation. Suppose the small object of mass m is a distance r from the center of planet bigger mass m. The force of gravity on this object is given by Newton's law of universal gravitation, g times m over r squared. We can also say the force of gravity is F equals mg, where g is the planet's gravitational field strength at a distance r from its center. There aren't two types of gravity. These are two equations talking about the same gravitational force. So we can just set them equal to each other. And here it is. F equals F, yet again. These are not different gravities, same gravity. F is still a force. We can set F sub big G equal to mass times acceleration, because a force is a force. Setting the two equations to each other, we get mg equals gmmr over r squared. Canceling out the little m's, we get g equals gravitational constant times big mass, mass of the bigger object, divided by r squared. Note the gravitational field strength of a planet depends on the mass of the planet and the distance from the planet's center. If you plug in g to be 6.67 times 10 to the negative 11, the Earth's mass and Earth's radius, guess what you get for little g? 9.8. Closest you get to a gravitational field equation on the AP Physics equation chart is going to be this little g equals big F over little m. It's just the same thing as Fg equals mg, solved for g. But you know that big Fg equals gmmr squared, so you can just substitute that there, and it's the same exact thing. Now let's say we have a new planet that has twice the radius of Earth. What would the gravity on this new planet be? The answer depends on whether this planet has the same mass or the same density as Earth. If the mass is the same, then we use that equation that we just derived. Twice the radius means 1/4 of the gravitational field strength because of that inverse square law. But if the density of a new planet is the same as Earth, then the new planet also has a different mass. Because if the density is the same and the mass is bigger, or the radius is bigger, then that means you have more atoms there to weigh. In physics, we use the Greek letter rho as the letter for density. This is because we can't use the letter capital D, which stands for distance. We know that density equals mass over volume. Density equals mass over volume. But a better way to write this equation is mass equals density times volume, because density and volume are independent of each other. Volume depends on how much matter there is, and density depends on what the matter is made of. So if the new planet's radius is twice the Earth's radius, the new planet's mass is greater because the volume is greater. Here's an important rule to know about spheres. If the radius of a sphere is multiplied by n, then the sphere's volume is multiplied by n cubed. This is because the volume of the sphere is 4/3 pi r cubed. So you have the sphere, which is how big the container is, and then you have the volume, which is how much stuff you can put inside the container. If the radius is doubled, volume is multiplied by 8, and so on. So our planet, with double the mass of Earth, has 8 times the Earth's volume, because mass equals density times volume. If the planet has the same density and 8 times the volume, the planet has 8 times the mass. So now, going back to our equation, G equals big G, big M over R squared, we said the planet has twice the radius, so 2 squared, so we know it's going to be 1/4 over here for the little g. Then we also said with the same density, twice the radius means 8 times the volume and 8 times the mass. This means that g is multiplied by 8. So you have 8 in the numerator and 4 in the denominator. It's going to be twice Earth's gravity. 19.6.